I'm Ross Bagurdes. This presentation is talking about TLS and data loss prevention. I want to kind of look behind the green lock and see what's happening here. How many people are using or are administrators for some type of DLP device already? Okay, a couple of you. Who has no idea what DLP is? What's that? Tape backups, yeah, right, yeah, yes, or those really nice TVs with the spinning mirrors on them from 15 years ago. Anyway, so data loss prevention, right, is the new way of snooping in on traffic. This is not actually that new, though, right? Because back in 2009 or so. We saw the first implementation of somebody implementing a man-in-the-middle attack on HTTPS, where they just took the HTTPS connection, hijacked it, and then gave the client pure HTTP data. So before we get into all of that, though, I want to give a little bit of background and introduce myself. So I'm Ross Bagurdes. I got my start in IT. Playing around as a kid with a TRS-80, right? And it just, my love for technology has just continued to grow and grow and grow. I actually have a structural engineering degree, and I quickly abandoned that because I started my career in the 90s, right when there were no IT engineers. So I was the guy who was curious about the technology. I would go play with it, accidentally break something, then have to fix it, and somehow I became the hero of the network, and that got me promoted. So I continued to break networks and fix them, and now today I spend most of my time not so much in engineering, although I do a lot of engineering consulting. I spend most of my time as an educator, and I just left Madison College in Wisconsin. As a full-time instructor, I was teaching data networking and firewalls and security, and now I do all of my work with Pluralsight.com. Does anybody use Pluralsight in their organization? Okay, one of you? A couple of you guys? Pluralsight is a platform for developer training, infrastructure training, cloud, and networking, and I do all of their Network Plus, CCNA, and Wireshark training, and most of my Wireshark stuff is introductory up through some a TLS course that I have up there as well. So if you are interested in learning more about Pluralsight or you want to see some more of my courses, I have some trial cards that I can hand out later on. But enough about this. Let's move on to the interesting stuff, right? So the goals for this session, what I want to do is I really want to start with some basics. And I realize that most of you in here already know how basic data encryption works, but I need to set a foundation so that we can get to the point of understanding what's happening with DLP. So we're going to look at encrypting data. I want to look at the Diffie-Hellman Elliptical Curve Key Exchange. And I want to talk about how that works. All right? And my experience with this is trying to learn how to educate others about it is you either have to have a master's degree in mathematics or spend so much time with working with protocols that deal with this type of encryption and key exchange methodology that you really, you just become familiar with it. So I tried to boil this down to the basics so that we can understand what's happening here. I think this is an important part of the conversation. Next, I want to talk about certificates and their role, and then we're going to get into data loss prevention and how that works. And then I'll explain my setup and how I collected some information about that, and then we'll look at some captures. And I want to take a look at the certificates on both sides of our data loss prevention appliance and see how the client doesn't notice necessarily that you're man-in-the-middling the traffic, and we can see exactly in Wireshark how we can analyze that. And a lot of that's thanks to Peter here. So let's just start with web browser encryption, all right? We're going to start with TLS 1.2. I didn't realize that this is a 90-minute session. I think a lot of them are 60-minute sessions, so I may be a little bit short on material. But that's not a bad thing because I have some other stuff we can talk about as well if you want. So with web browser encryption, TLS 1.2, really, we're working with two things here. We're negotiating an encryption session, and the negotiation of the encrypted session is happening with either SSL or TLS. What's the difference? SSL is the old name, right? Yeah. Does anybody know why they changed the name?
I think Microsoft was one of the drivers.
Microsoft forced them, right? So back in the 90s, the first web browser, well, not the first web browser, but the first commercial web browser was Netscape Navigator. And Netscape Navigator is one of their first customers. What they did is they said, hey, we need some way of encrypting the data. We want to do some e-commerce with these browsers, and we want the data encrypted. And SSL was born. First versions of SSL were pretty much junk. They were easily compromised. And then Microsoft came to the table, and this was during the browser wars, and they said, hey, we want encryption in our Internet Explorer as well, and we're going to write an RFC about it. And we want nothing to do with what Netscape has to say about it. We don't want to use Netscape's name for this, so they abandoned SSL, and they called it TLS. Right? So this is happening in the 90s already. And so they're one and the same. We use them interchangeably. It's a very recent update to Wireshark where you can actually interchangeably use now SSL or TLS to actually search for this traffic inside of Wireshark, which is really brilliant. So the idea there, though, is we're going to negotiate an encrypted session using SSL or TLS, and then that is going to allow us to use some encryption protocols here. Either the asymmetric protocols, RSA, Diffie-Hellman, and Elliptical Curve Diffie-Hellman, and the symmetric protocols, Triple Des, AES, and SHA-SHA-20. True or false, the public key is used to encrypt our data in HTTPS, and the private key is used to decrypt it.
Wrong. False.
That is false, right? Why?
Because the asynchronous key of the certificate is just used for the handshake, and then a synchronous key is created, and this one is used for encrypting the content.
Exactly, right on. So if you didn't hear that and you didn't catch this, there's a myth. If you try to read about how this encryption works on the internet, a lot of engineers or authors on blog posts will get tripped up about what's actually happening in this transaction. And they'll start off saying, oh, it's so easy. In HTTPS, you use the public key to encrypt all of your data and the private key to decrypt it. And it's not entirely false, except it is false when we're talking about the bulk data that we're moving, right? So TLS is not actually using this methodology to encrypt data. Let's see how it actually works. So data encryption basics. When we're using HTTPS, we're literally using symmetric encryption, right? And symmetric encryption, all we're doing is we're taking an unencrypted message, we're putting it through some formula along with a secret key that gives us our encrypted message. We send that secret message across the wire, and then we use the same formula and the same key to decrypt that same message to get our decrypted message. Right now, the problem though, right, is this key. We can't have both sides have the key if we send the key across the public internet, because that means that everybody would have that key. So we need a way of exchanging that key without anybody knowing about it. So when we're doing our bulk encryption of data here, we're doing symmetric key encryption using either AES or SHA-SHA-20. I don't have Triple Des on here anywhere because most servers no longer support it, and that's probably a good thing. I think if we were having this conversation at like Black Hat, we could probably argue about the integrity of AES, but we're not. We're here. We're realists, right? We have to get our jobs done and keep the websites running. So most of the captures that I have seen in my experience working with HTTPS are using AES. Not many are using SHA-SHA-20. The key exchange, though, is really this is the fun part, right? For me, this is the most exciting part. So in our key exchange process, right, we're working with two protocols at this point, TLS 1.2 and 1.3. we really don't want to be using anything prior to 1.2 at this point. There's vulnerabilities involved in them. 1.2 and 1.3 are the way to go. We get a lot of efficiency when we're using TLS 1.3. And there's another session tomorrow at the same time in the same room from Peter over here, who's going to talk about TLS 1.3 in a lot more detail than I will. All right, so when we talk about TLS 1.2, we have several key exchange methods we can use. We can use RSA. It's Rivis Shamir Edelman. This is the public key used to encrypt and the private key used to decrypt. Right, but the problem with RSA, does anybody know the problem with RSA? About 10 or 12 years ago, somebody was able to use modern equipment at the time. It took about 6 weeks, and they reversed it. They reversed the encryption for RSA. So it's not that RSA is completely awful and broken. It's that there's potential that you can decrypt the traffic if you have enough computing power and long enough time. The other piece here is that Diffie-Hellman, if you start doing captures, going to common websites and you start looking at the captures, not many people are using Diffie-Hellman. Not many servers are actually using Diffie-Hellman to encrypt or to do the key exchange anymore. Most of our servers are now using elliptical curve Diffie-Hellman, and there's a reason for that. We get a much stronger key with much less computational need, right? So you get this really strong key with not as much computing power as you would need for Diffie-Hellman. And this makes everything more efficient in the long run. Additionally, once we get to TLS 1.3, we don't get any choices. You get to use elliptical curve Diffie-Hellman to do your key exchange. That's it. So let's take a look at what elliptical curve Diffie-Hellman looks like. Now this operates a little bit differently. The basics are the same in both, but TLS 1.2 and 1.3 implement how the key exchange happens a little bit differently, and 1.3 is way more efficient. We're going to look at 1.2 here. So the elliptical curve, what we do is we take this curve, right? It's just a formula, basic algebra formula here that we use for our curve. And in elliptical curve Diffie-Hellman, we have 6 different curve types that are named that we can use. So the client and the server are going to, in the conversation of negotiating a session, they're going to negotiate which curve to use. And typically what this means is that the server is just going to send the curve type to the client and say, we're using this curve. All right?
Is it mandatory for both sides that they support all these curve types?
No.
Can they?
They're going to negotiate. Oftentimes the client and the server, the one that I see used most often is either one of the top 2. But yes, they will negotiate. If one end says, I want to use this type, and the other says, I can't support that, they'll change to a different type.
Would there be a fallback then?
No, I believe the ones that I've seen, and this is the ones that I've seen will oftentimes send 2 different curve types. Okay. So in TLS 1.3, what I've seen is the client actually initiates the curve type selection. And I've seen the client more than once actually send 2 curve types so that it can say you can use this one or this one. And I have not seen yet a case where it had to renegotiate because one end didn't have the right curve type yet. So we're going to pick the curve type. Once we pick the curve type, we then draw a line through the curve, and that's going to select 3 points. The curve type plus these 3 points, this is our public key, or at least part of our public key. The next thing that happens is the server is going to take that curve plus the 3 points, and it's going to mathematically combine it with a private key. And when we do that, we come up with a number, right? And this number is the second part of our public key. So we take that number plus our curve type and the 3 points. This is what gets sent over to the client. All right, now the client is going to grab this information, and it's going to do basically the same exact calculation. It's going to take the curve type that was known, that everybody knows. It's going to take that curve type, combine it with the private key, and it's going to come up with its own public value that it can exchange. Now both the client and the server have used the curve and their private keys to calculate this number. The client sends its number over to the server. They then take these two numbers, combine them again with the private key, and that's what gives us symmetric keys on both sides. Right? Diffie-Hellman, if you look at how Diffie-Hellman works, it works almost identically to this. We're just not using curves in there. We're using P and G values, some very large prime numbers. Here we're using this fancy curve to do this instead. So this is how we get our keys on both sides. What's something that I haven't mentioned about this key exchange process? What isn't in the process that might be an RSA encryption? The certificate. We're not using a certificate here. We're using it, we're kind of using it, right? It's involved in the process, but at this point in the conversation, when the client and the server are exchanging, the certificate is not actually involved here. And maybe I'm getting ahead of myself. Let's find out. So I am getting ahead of myself. So we have our key exchange process, right? The key exchange process that we're using, elliptical curve Diffie-Hellman, allows us to do symmetric key encryption with our data encryption. This allows us to send our username and password using AES encryption from our client to the server. The last component of this is handshake integrity, right? And there's components in the handshake integrity that are designed to prevent a man-in-the-middle attack. So in order to do the man-in-the-middle attack and get our data loss prevention to work correctly, we really have to trick the sessions into having handshake integrity in a way that makes the client unaware that this is happening. And that happens in a couple different ways. The last way here is with server authenticity, and this is where the certificates come in. All right, the certificates, I think if you're in IT, this is relatively common knowledge, but let's just go through it briefly. For certificates, we have a certificate authority. As we talk about this, I want you to think about the level of trust involved with certificates that allows this system to work well. Because if we really start to think about it, we just have to, it's pure trust based that the organizations that are running the certificate authorities and the organizations that are validating the certificate authorities are actually doing their job correctly. Because if we don't have any idea if WebRoot is actually doing their job correctly, right? We have to put all of our trust in third-party organizations to make sure that certificate authorities are working correctly. This is going to become really important with data loss prevention because, we'll see. I'm getting ahead of myself. So we have a certificate authority issues the root cert. The root cert is used then to calculate an intermediate cert. The intermediate cert is used to calculate a server certificate that will go on our web servers. We have a validation process that we can use to say, oh yes, the server cert, we can run a calculation and validate it and say that, yep, it was issued by the intermediate cert, that the intermediate cert was issued by the root certificate. We need to install that intermediate certificate on our workstation, and this happens typically automatically, right? Our operating systems will go to trusted authorities to say these are the valid certificate authorities that are okay, and we'll install those certificates on our workstations automatically inside of the operating system. Firefox and Google have their own versions of this as well. So when you install their browsers, you're installing a list of the intermediate certificates as well, so that when we browse to an HTTPS site, and let's say we're going to pluralsite.com here, and we send this certificate over to the client can then validate that the intermediate cert, with the intermediate cert, that our server cert is authenticated. Yes?
I thought the client and the operating systems only have the root certificates, and that the intermediate certificate must be served by the server with its server certificate.
Would you give me some freedom to say that we're?
It depends.
I don't want to say it depends. I'm using a bit of loose language here to describe the process. Typically the root certificate isn't actually, from my experience, the root certificate doesn't actually get installed You get a piece of the root certificate, or you get the intermediate certificate that gets put onto the client. But I'm willing to be wrong about this, if that makes sense, all right? In my experiments, I've been able to actually install intermediate certificates and have them validate the server certificate with that. Okay. So we have that validation. Are the certificates used to encrypt? Kind of. When we are using RSA, yes, definitely. When we're using Diffie-Hellman, the P and the G values are included in that certificate. And the P and G values in that certificate are then used to do the Diffie-Hellman key exchange. When we're using elliptical curve, the certificate that we exchange is used to authenticate the server. It's not actually used in the encryption. The elliptical curve part is independent from the certificate for the most part here, all right? Let's talk about data loss prevention then. Man-in-the-middle attacks, SSL intercept, right? These are all effectively the same thing. Data loss prevention is just is a way for organizations to protect their intellectual property. So when we are sending emails and browsing websites, possibly building reverse SSL tunnels into our network, data loss prevention allows us to inspect that, but effectively it's a man-in-the-middle attack. And what's concerning about this is how it happens and who can do it, right? So in a network, we're going to have a client and a server again. This time we're going to put a DLP appliance in the middle. And the DLP appliance can either be a device inside of your network in your internal network going outbound, or I've seen DLP appliances, right, that are cloud-based now. So those cloud-based ones just redirect the traffic to the cloud. It's actually what got me fascinated about this is a good friend of mine works for a genetics company in Southern California. He brought his phone to work. No, he was browsing his laptop. He's browsing the web on his laptop, checking his Gmail account, and Google sent him an alert saying, you're coming from an IP address that is not where your computer is located. Is this legitimate? And it took him a while, and he went back and looked, and their organization was actually using a DLP device. And it was a cloud-based one, so all the traffic was just simply getting redirected out to this cloud-based device. And what was happening here is that cloud device was building a session between the DLP appliance up in the cloud and the server at Gmail. Gmail was seeing the IP address of the DLP appliance. Now, if the appliance is right inside your organization, this is no big deal because the IP addresses are going to be consistent. When we have our DLP appliance out in the cloud, the source IP address for our message is actually going to be the DLP appliance. So what Gmail sees is the IP address of DLP and not of the client, not of the source of the client. The client, on the other hand, sees a source and destination IP address of itself and Gmail, right? So from the client's perspective, when we do a capture here, we see source and destination of the client to the Gmail server. It appears to be end-to-end encryption, except there's problems here, all right? There are mechanisms built in. There are mechanisms built in here to allow this trusted certificate to validate the authenticity of our server. And there are even more mechanisms built in now. Since 2009, when SSL split first came out, there's mechanisms in place now inside of HTTPS and TLS that prevent us from just taking the certificates that we got here and moving them over into our other session here. So the question is, how do we get a trusted certificate session between our DLP appliance and our client? Right, and this involves trickery now. This is where all the trickery comes in that is a little bit concerning when we're talking about man-in-the-middle attacks on HTTPS. So in order to get that trusted certificate now, we have to build this TLS session between the server and the DLP appliance. That's no problem. What we're going to have to do, though, is our DLP appliance is going to have some type of certificate authority involved, where we have a root certificate, an intermediate, and a server. You don't necessarily, well, we're going to have a certificate chain so that the client has something to validate against. But what's going to be the problem here? Well, the problem is that the intermediate cert that we generate from the DLP appliance has to be trusted. So how do we do that? Well, in the case of an organization where you're a genetics company and you want to make sure your intellectual property does not leave that organization, you're going to have administrative rights on that client. So you can push down, in addition to what the operating system pushes down, you can push down another certificate to validate your server certificates. So we can push down an intermediate certificate or a root certificate onto these devices. We can push it into Chrome and Firefox through group policy, so that now when we build the TLS connection, we can actually validate our certificate. So what happens is the server sends its certificate to the DLP appliance. The DLP appliance is going to regenerate a brand new certificate, and it's going to look almost identical to the certificate it received from the server. It's going to have all of the names and all of the fields are going to be exactly the same as they were for the server. It's just going to be generated from a different certificate authority, right? So the DLP appliance here is just regenerating a certificate, but it has a different chain attached to it. So when that chain reaches the client, typically, if you do not have the intermediate cert installed and trusted on your browser, you're going to get an error saying, this isn't trusted, you're being man in the middle. The moment that you install that intermediate certificate, though, on your client, all those worries go away, because from the end user's perspective, unless you are deeply looking for this, doing Wireshark captures or looking into the certificate information in your browser, you're never ever going to know that this happened, right? Because from the client's perspective, it got a certificate that had the right server name on it, which is what HTTPS is expecting, right? The client went to pluralsight.com. It's expecting a certificate from pluralsight.com. If it doesn't get that, it's going to say, ooh, something's wrong here. But since it got a certificate from pluralsight.com, it validated it against its intermediate certificate installed on the workstation. It's good to go. So the client observes end-to-end encryption.
Which CA assigned this intermediate?
It depends upon how it's set up. When I set this up in my lab, I'm using just Ubuntu Linux here and SSL split. So I used OpenSSL to create my own certificate authority. I created a couple certificates. I installed one on my client.
Doesn't it mean, I think so, that it must, the client must trust the certificate chain, so even the root CA?
Yes. Right. Yes, correct. Yes, and in this case, I'm putting the intermediate here, but I did also install the root certificate on there as well, which probably answers your question as well. So yes, I have both certificates on there. Thank you. So our client is observing the end-to-end encryption, but in the middle we have unencrypted data. This brings all kinds of questions to me, right? It makes me wonder what government authorities are doing, right? An organization like the NSA in the United States. Do they have a trusted certificate authority that can spoof this at a deeper level and decrypt any traffic leaving the country or even internally in the country? It's possible, right? But we have no evidence of that necessarily right now. My questions of this are, how long can we use these certificates to validate the authenticity of our servers to prevent this actually from happening? How do we guarantee end-to-end encryption? Not sure how that's going to happen yet, but I expect over time we're going to see some other mechanism built into TLS that's going to allow us, TLS and HTTPS, that's going to allow us to validate that the server that we're connecting to is who it says it is.
Isn't there any mechanism that in the application at the workstation or on the client side, there will be some releases of the fingerprints of the certificates, like from the bank, that they say, okay, this is our certificate of the server, this is the fingerprint, and whenever you download any application client for telebanking for something, then this application knows which fingerprints are trusted.
Certificate binning, right?
Yeah.
For the apps, if the client is not a browser, if the client is really an app
Right.
application, then you get big troubles with the man-in-the-middle approach because they are doing what you said, and then you have no chance because they are not checking the chains, they are just checking the integrity of the original certificate.
Right. Absolutely. Yeah. This situation definitely has limitations, right? Which is why I was limiting to HTTPS for this presentation. But you're correct. Yes, there is the fingerprinting that can happen with HTTPS. We can manipulate the header information enough to trick both ends into thinking that it is secure. But yes, once you're talking about web apps, yes, everything changes. And it gets a lot more sophisticated at that point, certainly. Yeah.
So the DLP appliance will be generating a certificate for each of the servers that the client wants to.
Correct. On the fly. Right? So yeah, you go to Gmail, the DLP appliance creates a Gmail certificate, sends it to the client with a different chain of authority. You have, you go to Facebook, same thing, right? And this keeps happening.
There were approaches previously for creating the correct certificate or getting the private key from the certificate via hash collisions. This was working for MP5 hashes in some circumstances some time ago.
Okay.
They had some clusters where they used the online creation of a certificate by using the hash collisions because an hash, MP5 especially, is not unique. You can have several different inputs leading to the same MP5 hash, and that's what they used for creating a real original certificate. But it was 10 years ago or so.
Right. Yes. A lot of this
They all switched to SharkFest, and so it's not possible anymore.
Right, and there's possibilities too. If you did have the server's private key, you could generate real certificates too, of course, right, on the DLP appliance.
You are gone before this certificate.
Yep.
Everything would work, but it's not possible anymore.
Right. So let's take a look at a couple captures. I appreciate all the questions. I think some of you may have been hoping for more depth than I'm offering in this particular presentation, but I hope I'm able to offer some insight into what's happening with DLP, what we're doing here. So let's take a look at a couple captures. I've done a capture on both my client and on the outside interface of my DLP appliance. And really what I want to take a look at is the certificates here. Yeah.
Is it possible to switch off the first light throw?
I think I can make it extra dark or not, or extra light. I think it's one or the other. Well, there's some mood lighting for us. Yeah, when I came in and Christian was in here, it was pitch black like this, and I'm like, oh. Okay, so I said let's take a look at the DLP appliance first. So we'll start with my connection between my DLP and the server. And we're looking at basically the same transaction, just one's happening between the DLP appliance and the server, and the other one's happening between the client and the server. If we take a look at the handshake here, we have the client hello, the server says hello, and then the server sends the certificate. So we have client hello, server hello, client sends the certificate. If we drill into this, take a look first. If we look at the key exchange, we'll see that it is using elliptical curve Diffie-Hellman. And you can see the parameters in here, SECP 256R1. And then there's our public key information, which includes the 3 points on the curve as well as that calculated value. If we go up and look at our certificates, we get our certificate chain. The first one here is from, so I went to pluralsight.com, so I have star.pluralsight.com here for the name on my certificate. It is signed by GoDaddy. And we get the chain, the certificate chain to come along with that. So here's our GoDaddy certificates that come along with it, including our root certificate. If we look at the same transaction then on our PC, client hello, server hello, certificate. We drill into this. There's our Pluralsight certificate again, right? Same exact common name, same organization ID and whatnot. But if we drill in to see who issued it, it was issued by my bogus name, SSL proxy.sslsplit.local. That sounds legitimate, right? In Wisconsin, Madtown. Organization name is Bad Cert. Organization unit name, stop looking here. Yeah.
Is it possible that you also can spoof the serial number? That the serial number might be exactly the same as the original one?
That is a question I have, to be real honest with you. It's something that I have been working for weeks on to try to mess around with, right? Because I have the same exact question as well, because there's so much you could do with that by doing that, right? You could almost, if you really wanted to, the idea that is in the back of my head is, what if you could take all those certs and somehow spoof it and dump it and get into the new connection, right? Yep. So you take all of your certificates in the chain and you just move it over into your client to DLP server connection and make it work. It doesn't. All right, so this is basically the Wireshark connection here between our DLP appliance and our client. It can use its own version of encryption as well. So if we look down, server key exchange. In this case, we're actually using the same curve type. We have our own public key now that was generated from the DLP appliance. Now, the DLP appliance is using its own private keys to generate that certificate, of course. Or, to generate that public key information. More information about this right now. Tomorrow, like I said, Peter Wu is doing a SSL TLS decryption, uncovering secrets right in this room at the same time, 4:30. I highly recommend coming to his session. He's a core developer for Wireshark and has adapted a lot of the why am I blanking on the word? Sorry. Dissectors, thank you. He's adapted a lot of the dissectors to accommodate the updates in TLS, which are constantly changing. If you're interested in more of my work, I have a bunch of courses on Pluralsight, including analyzing and decrypting TLS traffic. To wrap up, we looked at encrypting data, right? We looked at the elliptical curve key exchange. We looked at validation and encryption with certificates. We examined data loss prevention with HTTPS, and looked at it in Wireshark. Do you guys have more questions for me? Yes, sir.
I think I've heard something that TLS intersection man-in-the-middle tag is not compatible with TLS 1.3 anymore.
This is possible, but I'm not sure. Peter, do you have a comment about that?
So in TLS 1.3, there's a new mechanism to allow client to detect a downgrade. So in TLS 1.2, if like the certificate is rebased, well, the client could not really notice it, well, except for the certificate. In TLS 1.3,
I'm sorry to put you on the spot.
so your question is whether it's possible or not to perform man-in-the-middle with TLS 1.3?
Exactly, because I think that one, I'm not quite sure at the moment, to be honest, but I thought that this is not possible with TLS 1.3 anymore, and this is why the inventors of TLS 1.3 are that happy, because that other countries cannot accept their global public
Yeah,
anymore. But of course, looking from a data loss prevention, looking for an enterprise, you must middle those connections to have a look anyway. So it's getting harder. So
Yeah, and I believe, if I remember correctly, there is a presentation online from Cloudflare
exactly.
that talks about this.
Yes.
He doesn't go into the detail at all, though, about it, if I remember correctly. He does say that there is detection for that downgrade, like Peter was saying.
I think that guys from Riverbed also have some information on this.
You have some information on this?
Yeah, I visited the presentation of them, which was really fancy, and they mentioned something about basically storing all your data, and then you get decrypted later. So if I remember correctly, they said it wasn't possible to do it on the fly, but afterwards you should be able to do so.
All right.
But I think it requires a rather big wallet as well.
Yeah, as something there. So thing I was thinking about was an anti-downgrade signal. So in TLS 1.2, if you get downgraded, well, the server, like the client, will maybe retry connection with a lower version. With TLS 1.3, if the client pretends to only support, say, so the client advertises support for 1.2, 1.3, but the server should use the R3 on 1.3. But if you have like man-in-the-middle, that's stripping off the TLS 1.3 like support, then the server, in this case, will send a special client, a special server random value that will indicate like, oh, this was actually a downgraded connection, protocol-wise. But your question was whether TLS 1.3 makes man-in-the-middle like harder. No, it works the same as TLS 1.2. You can still have a man-in-the-middle that has a valid 1.3 control 1.2 conversation with the client and a valid 1.3 conversation with the server. That doesn't change. You still need to check the certificate. What did change is that RSA encrypt, like the RSA Key Exchange is no longer supported. It was dropped completely. That is probably what Cloudflare and by TLS 1.3 makes this like passive attack impossible.
Yeah.
There's this new thing that's called certificate transparency,
Yes.
where you actually publish your certificate into some signed blockchain or something like it.
Mm-hmm.
And when that, or if that is implemented in applications, it will be very hard to do.
It's a little bit harder, as I understand it. The tool that I'm using, SSL Split, is able to get around that by how did it say it got around this? It sent some spoofed messages back to indicate that it wasn't going to check that, and it allowed the connection to continue.
So the application.
Yeah, you'd have to be down at the application level, so if like you're using an app versus HTTPS, yes, I think there'd be a difference there. Yes, sir.
Ross, do you know whether or not it's mandatory to have the complete certificate chain in this server certificate? When you need to in there, or is it just possible to have intermediate?
I believe you need to have the root in there as well, but I have to play around with it some more.
Because I've seen SSL interception working, and they were dropping the actual root certificate in the server certificate that's proved, which made, for example, Java applications fail, whereas the browser would still accept it.
It still accepts it, yeah.
I'm just trying to figure out whether that's a bug or a feature.
Yeah.
Very close.
Yeah, sorry, that one I don't have all the answers for you in that one. Yeah.
The question is whether you need to have the root certificate in the server configuration that like the DR server?
No, in the actual server certificate, there's the path to the intermediate CA and the root CA.
Yes.
Usually, the question is whether the root CA is mandatory in that server certificate.
Or it can only be included because the purpose of sending off certificate is to allow the client to figure out a trust path, so you can determine whether or not to trust this certificate, like the end lead certificate that was sent by the server. So you can send the roots to CA, but it will not help with this trust path because the client is supposed to have this root CA already.
You're talking about in here, though, right?
Yes.
This piece?
Yeah, also when you look in the certificate, the actual certificate, you see the path to the intermediate or root CA.
Oh, right.
Or there's a field.
Yeah, right, because the certificate here, yes, if you look at the certificate, it says who it's issued by.
And sometimes it includes both, and sometimes it's just the intermediate that's contained.
We can deliberate, but it makes no sense. It's a key point here. So we can have a complete chain of trust delivered by the end system, but it makes no sense because you have to have some point of trust, and it's really the root certificate. It has to be installed on the client.
Exactly.
So if there's just, it makes no sense.
Yeah, the thing in the certificate request, there is no need for the client anymore to store any certificate.
Yeah, and there's no trust.
Obsolete.
If you trust anybody,
But
if
we
you
have to
the
just store the
root
intermediate, right?
certificate, if you trust it, there's no chain of trust, and no way to validate.
The last element in the chain must be some trusted stuff on the client.
Must be logins, otherwise it makes no sense. Many people do this, they send the root certificate in their server chain, but it makes no sense. You just need an intermediate that completes the chain of trust to your server.
So what I'd like to do at this point is I'd like to wrap up. If you have questions that you want to talk about or you have information for me, I'd love to hear about it. If you want to talk amongst each other, that's great. I know we're ending the session a little bit early. My time, legitimately, my time got moved around over the last couple weeks, and the earlier sessions were a little bit shorter. So my apologies about that. It is also the end of the day. So, and I see some tired eyes. So, I'm sure a full day of absorbing Wireshark, looking at Wireshark is intense. So, thank you very much, everybody.